Let's think about this. What is the shape of the universe? You might have never thought of this question, but let's take a moment to consider it. What is the overall shape of the universe on a grand scale? I've seen the universe portrayed in many videos and images, often as a large, dark sphere expanding from the tiny point of the Big Bang. But let me tell you the truth straight away. The universe is not a three-dimensional sphere. Erase that idea from your mind, because those videos are just simplifying the concept for clarity. Now, think carefully. What could the universe's shape really be? Our Earth is roughly spherical, but the solar system is not. It is a very flat disk. The Milky Way is also a disk, but it has many spiral arms. Not all galaxies are disk-shaped, though. Take the spiral galaxy IC 2163, for example, which looks like a pair of big eyes. Or the SO 137001 galaxy in the Triangulum constellation, which resembles a giant jellyfish. There's no doubt galaxies can have all kinds of shapes, so it seems that the universe itself could have any shape. If you're an ambitious cosmologist, you wouldn't want to just guess blindly. But since we can't fly out of the universe to take a picture of it, the only thing we can rely on is theory to narrow down the infinite possibilities to just a few, ideally. Only one. One theory has already narrowed it down to 3 possible shapes for the universe, and we're getting closer to identifying the final answer. This theory not only shapes our understanding of the universe's form, but also determines the very speed of time itself, whether time even exists in a meaningful way. Today, I want to talk to you about this idea, which might sound familiar at first, but is rarely discussed in detail in science. It's called symmetry. Have you ever thought about how the deep, underlying rules governing our Earth, the starry sky above, and even the vast universe are all hidden within 2 seemingly simple statements? Let's start with these 2 sentences. Renowned physicist Richard Feynman once said that if he had to summarize the most important discovery of modern science in 1 sentence, he would choose, "The world is made of atoms." This is because many of our understandings of the universe are based on the properties of atoms and the theories of how they interact. Many famous modern scientists believe that if they could pick another sentence, it would be, "Symmetry is the foundation of the laws of the universe." A joke in the scientific community goes like this: if all of human civilization were destroyed, and we could only live behind 2 sentences for future generations, those 2 sentences would be, "The world is made of atoms" and "Symmetry is the foundation of the laws of the universe." These 2 sentences would save the next emerging civilization hundreds of years of exploration. Over the past few centuries, countless revolutions have taken place in science, and the most vibrant discoveries all have one thing in common. They focus on the invariances in nature, the aspects of the world that stay unchanged under different conditions. This concept of invariance is what physicists call symmetry. Of course, symmetry in our daily lives can refer to something as simple as the left and right sides of an object. But the kind of symmetry that physicists talk about is much broader. In many important scientific breakthroughs, symmetry has played a crucial role. Let's start by discussing one type of symmetry that you're probably familiar with: geometric symmetry. If you take a cue ball and spin it, or rotate a plane disk around its center, you'll notice that these objects don't seem to change while rotating. You can also take a snowflake and rotate it by a certain fixed angle, and it'll look the same, even though it's rotating. You might think that the symmetry of these objects is simple, but the concept goes much deeper. In physics, symmetry refers to a broader idea. Any transformation, whether real or imagined, that doesn't cause a change in the object, is considered a symmetry of that object. The more types of transformations an object can undergo without changing, the more symmetry it has. For example, a perfect sphere, like a cue ball, has high symmetry because no matter how you rotate it, it looks the same. A cube has less symmetry because it only maintains its shape when rotated by 90 degrees around certain axes. The letter A has even less symmetry, only remaining unchanged if it's flipped 180 degrees along its vertical axis. But symmetry in physics is not limited to simple rotations and reflections. We can think about it in more abstract ways. The key idea is that no matter what transformation you apply to a physical system, whether in space or time, the fundamental laws that explain the physical phenomena we observe must remain unchanged. For example, let's say you're a gymnast preparing for the Olympics. Over the years, you practiced every move so much that you instinctively understand Newton's laws of motion, like how much force to apply to do a front flip or a 720-degree spin. When you fly to the US for the event, you expect the laws of physics to stay the same. Whether you're on Earth or anywhere else in the universe, Newton's laws don't change. This is what's known as translation symmetry or spatial invariance, the idea that the laws of physics are the same no matter where you are in space. This principle holds not only in Newton's laws, but also in electromagnetism, Einstein's theory of special relativity, and quantum mechanics. Similarly, another type of symmetry, time symmetry, suggests that the laws of physics should remain unchanged no matter when they're applied. Whether you're studying the universe's past, present, or future, the laws should be the same. This symmetry gives us a foundation for understanding time as a consistent, measurable phenomenon. Now, let's think about the more complex idea of time. We know from relativity that time passes differently depending on your speed and the gravitational field you're in. If you travel close to the speed of light, your perception of time will slow down. But the question is, when we talk about the age of the universe, 14 billion years, whose clock are we referring to? This concept also depends on the symmetry of space-time and the way it behaves across the universe. Scientists have discovered that the microwave background radiation in the universe is remarkably uniform. This uniformity is critical because it supports the idea that the universe's early state was homogeneous, not dominated by massive, irregular objects like black holes. This evidence helps define time as a meaningful concept in cosmology. The universe is expanding, and as Edwin Hubble discovered in 1929, distant galaxies are moving away from us. The farther a galaxy is, the faster it moves away. This led to the conclusion that the universe began with a Big Bang. But the question remains, if the universe were expanding from an explosion, wouldn't there be a center to that explosion? No, because the expansion of space itself means that all points in the universe are equally distant from one another. This leads to the idea that the universe could be infinite in extent, with no boundaries or edges. And it could be either positively curved, like a sphere, negatively curved, like a saddle, or flat. The current consensus suggests that the universe is most likely flat, based on the critical density of matter and energy in the universe. The exact shape, whether it's spherical, saddle-shaped, or flat, is still being explored, but we are very close to understanding the final answer. In conclusion, the shape of the universe may be one of three possibilities: a positively curved, negatively curved, or flat space. This is a remarkable result, as it shows how symmetry, the idea that all points in the universe are equivalent, is a guiding principle for understanding the cosmos. The laws of physics are the same everywhere in the universe, which is why we can study distant galaxies from here on Earth and understand the same fundamental principles. Symmetry is a foundational concept in modern cosmology, and as we continue to explore the universe's mysteries, it remains central to our understanding of space, time, and the laws of nature.